In this presentation, I'm going to cover the process abstraction. By the end of the presentation, I hope to have answered the following questions. Why is this abstraction necessary? What is a process? And how does the operating system ensure that processes are not able to access memory or files that they do not have permission to access? So first, why have processes? The operating system needs to run multiple programs at the same time across multiple users. All of the programs share the same processor, the same memory, and the same disk space. Despite this, the operating system needs to have some way to prevent programs from accessing resources that they shouldn't have access to. The operating system needs to ensure reliability, meaning one program should not be able to crash another program by, say, altering that program's memory. The operating system needs to ensure safety, meaning that untrusted programs should have limited scope in what they're able to do. For example, they shouldn't be able to access the hard disk and, say, overwrite the kernel. And the operating system needs to ensure privacy, meaning that a program should only have access to files which are owned by the user who ran the program. It should not be able to access other users' files. And finally, the operating system needs to ensure that the system resources are being allocated fairly between the processes, and you don't have one process which is hogging the resources and slowing down the entire system. To ensure these properties, the OS creates an abstraction called a process, where the program can safely execute without violating these properties. A process is the abstraction for protected execution of a program provided by the operating system kernel. Simply speaking, a process is an instance of a program, much like an object is an instance of a class. In order to ensure safety, the operating system designates operations as either privileged or not privileged. A non-privileged operation would be something like taking the values in two registers and adding them together and moving them to a third register. Whereas privileged operations would be things like accessing files, accessing memory that is not part of the process, or networking, for example. The OS ensures that only the kernel is allowed to have full hardware access and perform privileged operations. The kernel allows processes to perform these privileged operations through system calls, which are essentially APIs that the OS exposes to the user programs. When a process uses a system call, the kernel takes over the process, checks whether the process is allowed to perform the operation it wants to do, and then if the process is allowed, the kernel performs the necessary privileged operation and then returns the process control back to the process. The diagram on the left shows the way non-privileged entities interact with the kernel to perform privileged operations. The diagram on the right shows some of the system calls which are present in Unix and Windows. You can see that there are system calls for process management, file manipulation, communication between processes, and other things. The operating system has to manage multiple different processes running at the same time and needs to be able to switch the process that's running. In order to do this, it maintains a list of all of the processes which are running. And within the list, it contains entries called PCBs, or process control blocks. The process control block is a simple data structure which stores the necessary information about a process's state so that the operating system is able to stop processes and pick them back up wherever they left off. If we take a look at the process control block, you'll see that the process control block stores important process-related information such as the process state, which describes whether or not the process is running, ready, or blocked by, let's say, an I/O operation. It stores things like the PID, which is the process's ID number. It stores the stack pointer for the program. It stores the PC or program counter, which keeps track of where the process currently is in its executable file. It stores the important registers, so when a process gets stopped, it can copy the values from the registers into the PCB, and then when it gets restarted, it will be able to pick up where it left off. It stores the memory limits. For each process has a separate memory address space so that there's no memory overlap between processes. It stores memory pointers, which point to where the code is stored in memory. And finally, the PCB stores the file descriptor table, which is a list of files that the program has opened and has not closed yet. There are other things as well which can be stored in the PCB, such as pointers to parent and child processes, but these are the main ones. Finally, how is a process created? First, the kernel must initialize the process control block and allocate memory for the process. Then the kernel copies the program executable and static data from disk onto this newly allocated memory. Next, the kernel allocates memory for the execution stack, which contains function calls and local variables. The kernel also copies the program's argc and argv onto the stack. The kernel also needs to make a separate kernel-level stack for the process, which it will use for handling system calls and interrupts. Another section of memory is created for the heap, which stores dynamically allocated data. Anytime you call malloc, you're adding that data to the heap. And finally, the kernel adds a stub to the beginning and the end of the program. This stub invokes the main method of the program at the beginning, and once the main method returns, the stub tells the kernel to delete the process. Finally, I just want to acknowledge that most of the information and figures from this presentation were taken from the Operating Systems Principles and Practices textbook and from Operating Systems 3 Easy Pieces.